In this video, we're going to go through a couple of calculation examples for how to use the freezing point depression and boiling point elevation equations and that pesky Van Hoff factor as well. So in this one, we're told that cinnamon owes its flavor and odor to the compound cinnamaldehyde. What we want to know is, what is the boiling point elevation of a solution of 100 milligrams of cinnamaldehyde dissolved in a 1 gram carbon tetrachloride solution? Now, in this particular case, we're talking about boiling point elevation. So we are going to use the equation delta TB, the change in boiling point, is equal to I times KB times the molality of the solution. Now, in this case, cinnamaldehyde is not ionic, and actually carbon tetrachloride is flat out nonpolar. So even if it was ionic, carbon tet wouldn't separate it. So in this case, we know that I is equal to 1. And we are told that Kb is equal to 2.34 degrees Celsius per mole. So the only thing that was left for us to do is to determine the mole concentration of the solution, and then we can plug in all of the pieces of our equation. So for molality, we need moles of cinnamaldehyde divided by kilograms of carbon tet. For the moles of cinnamaldehyde, we have 0.100 grams of cinnamaldehyde. That's 100 milligrams divided by 1,000. We're going to take that. Its molar mass has been given to us here, 132.17 grams of cinnamaldehyde per mole. And so if I throw those into my calculator here, 0.1 divided by 132.17, I get to 3 significant figures, 0.000757. moles of cinnamaldehyde. Now, to find molality, I'm going to need to take those moles, 0.000757, and divide it by the mass, the kilograms of carbon tetrachloride, which would be 0.00100 kilograms of carbon tet. Again, 1 gram divided by 1,000 would give me 0.001. And so taking that 0.000757 divided by 0.001, I would get a mole concentration of 0.757 mole cinnamaldehyde. So there's my molality. I've now got a value for I, a value for Kb. Let's figure out the freezing point, or excuse me, the boiling point elevation. So the change in boiling point is equal to I, 1, times Kb, 2.34 degrees Celsius per mole, times the concentration, 0.757 mole. And if I follow through, my moles will cancel. I'll be left with just degrees Celsius. So 0.757 times 2.34 times 1 would give a boiling point elevation to 3 significant figures of 1.77 degrees. Now, keep in mind, that is the boiling point elevation. That is how much higher the boiling point will be for the carbon tetrachloride compared to its normal carbon tetrachloride boiling point. If we go back to the previous slide, we see that the normal boiling point of carbon tet is 76.8 degrees Celsius. So the boiling point would be 1.77 degrees Celsius plus the 76.8 degrees Celsius that is normally. To the appropriate number of significant figures, since we're only given one decimal place, 78.6 is going to be our boiling point for the solution. So we expect the solution would boil at 76.8 degrees, or excuse me, 78.6 degrees Celsius. Now let's take a look at our second example. All right, in this example, we're actually looking at freezing point. We're told about calcium chloride. Calcium chloride is a common additive, things that you put onto your road and onto your sidewalks in the winter to de-ice them. The question is, could calcium chloride melt ice at negative 20 Celsius? And for that, we have to make some assumptions. We have to assume that the solubility of calcium chloride is 70 grams per 100 grams of water, and that the Van Hoff factor in this case is actually 2.5. So if you recall from our previous video, we would have estimated that the Van Hoff factor here was actually 3 because we would get 3 ions per molecule. But because of the concentration here, we actually would anticipate that the factor here is 2.5. That is, that some of those calcium chloride ions actually come back together and remolecularize into calcium chloride molecules at this high of a concentration. So we follow the same protocol that we did before. Our change in freezing point is equal to I times Kf times molality. We are given the value of I. We are given the value of Kf. We need to figure out the value of the molality. Now, in this case, we are told that our concentration, 70.0 grams of calcium chloride, divided by 100 grams of water, well, we can spin that pretty easily into molality. We just need to fix the grams into moles. Molar mass will take care of that. And turn the grams of solvent, water, into kilograms, which also is pretty easy. So this is going to require a double conversion, two extra calculation steps. So I'm just going to put those in there right now. The first one we know is 1,000 grams of water in every kilogram of water. So that'll take care of the kilogram issue. And then we'll use the molar mass here, 110.98 grams of calcium chloride in every mole of calcium chloride. And so if we follow this all the way through, our grams of water cancel, our grams of calcium chloride cancel. I'm left with moles of calcium chloride per kilogram of water. That's molality. Do the calculation. 70 times 1,000 divided by 100 divided by 110.98 is going to give me a molal concentration of 6.31, which is high. We would expect it to be high since this is a saturated solution. And so now we put in all of these into our equation. The change in freezing point is equal to I, 2.5, times the freezing point depression constant, 1.86 degrees Celsius per molal, times the molality, 6.31 molal. If I do that calculation, 2.5 times 1.86 times 6.31, I get a freezing point depression of 29 degrees. And since the freezing point of the solution would be equal to the freezing point of water minus the freezing point depression, freezing point of water is 0 degrees Celsius minus the 29 degrees Celsius that we calculated, we would anticipate that the saturated solution would freeze at negative 29 degrees Celsius. The fact that we're asking if it goes to negative 20 degrees Celsius, the answer here is yes. We would actually anticipate that would actually be able to go further than that. For our last example, we're actually given something a little bit simpler. What is the boiling point of seawater where the concentration of sea salts is equivalent to 0.560 moles of sodium chloride per kilogram of water, and the Van't Hoff factor is 1.85? Well, we're talking about water here. Kb for water is equal to 0.51 degrees Celsius per molal. And if we see our equation, delta Tb is equal to I times Kb times m. Well, our I has been given to us, 1.85. Our Kb is 0.51 degrees Celsius per molal. And we are given a concentration, 0.560 moles of sodium chloride per kilogram of water. That's a molality. So 0.560 molal solution. My boiling point change is going to be equal to 1.85 multiplied by 0.51 multiplied by 0.560. So the two significant figures because of the kV, we're talking about a change of 0.53 degrees Celsius. The boiling point of the solution is going to be equal to the boiling point of the pure solvent, water, plus the change in boiling point. The boiling point, normal boiling point of water, is 100 degrees Celsius. And that's an exact value, so there are infinite number of sig figs there. The boiling point elevation we just determined was 0.53 degrees Celsius. So our anticipated boiling point would be 100.53 degrees Celsius. So with a concentration that small and a relatively low boiling point elevation constant, we wouldn't anticipate a large increase in boiling point, only half of a degree essentially. So this is how you do those boiling point elevation and freezing point depression kinds of problems. In our next video, we will start to look at osmosis and another phenomenon known as osmotic pressure. Until then, have a good afternoon.